So now I would like to invite Chirag Kar. Chirag is pursuing BSc in Mathematics from Shivnadar Institution of Eminence, Greater Noida, UP. His topic of presentation is Burnside's Lemma and its applications. So Chirag, over to you.
All right. Thank you so much, first of all, for inviting me over here, and thank you for giving me this opportunity. So, I'm going to basically be talking about something called the Burnside lemma, and which is a fundamental theorem in combinatorics and group theory. But more than that, I mean, I don't really want to start off with the theorem itself. So I'll start off with a rather simple problem. That is the problem of looking at squares. Now, here a simple idea. I want to color this square, all right, and I have with me two colors available over here. That is blue and red. Now, I'd like all of you to sort of pitch in from time to time and tell me which how to sort of go about it. So my plan right now is to just count how many possible ways are there to color this guy. Now, if for example I was just coloring without really wondering about whether there is any sort of symmetry or anything, if I was just doing it in the standard combinatorial fashion, it would basically be two colors present over here, two colors present over here, two colors present over here, and two colors present over here, which basically gives me 2 to the 4 is equal to 16 possibilities. Am I right? I'd like resounding yes if you guys agree. All right. Now, what is basically going to happen is that I want to modify this problem. We won't just look at, for example, we won't just look at coloring. We won't just look at coloring of this square. Um, just in any fashion, but this will be up to rotations. Now, here is a question for all of you. Well, how many possible colorings are present? If according to me, if I can obtain one coloring from another via rotation, then they are the same. So, as an example, let's look at this. So here we have three sides blue and three sides red. To me, this is the exact same, and I'm just going to denote it like this. This is the exact same as, for example, something like this. Okay, yeah. So this is what I mean. Now, here is a question for all of you. What I'm going to do is that I'm going to write out all of these colorings and then sort of try to, first of all, brute force my way through, how to sort of basically get at it. So, all right, let's begin. First things first, let's look at some cases, right? What happens if all of them are one color? Because I like blue more than red, I might as well just start with that. So the first color we look at is suppose they're all blue. All right, fair enough, no problems. The only way you can obtain anything else from this via rotations is just this guy over here. But let's make it a little more interesting. Suppose we introduce one side which is red, all right, and three sides blue. Now here, it's not just this one coloring which is sort of unique. I could also have something like this. I could also have something along the lines of this. I could also have this, and of course, completing all of these sides. And to me, all of these ones in the same line, in the same horizontal line, are the same. That is what I mean. So let's look at, for example, the other, what happens, suppose, and this is what happens when you have one red line. And this, I think, covers all the cases where there is exactly one red line. So let's see what happens when you have two red lines. Now, the case with two red lines is actually a lot more interesting because you can basically look at, either these guys being adjacent like this. So in this scenario, for example, you would just have these guys being adjacent. This is the same as this guy. which is the same, for example, as this, which is the same as, for example, is reach the same guy again, which is the same as this. First finishing up. So as I said, to me, they're all the same. They're all essentially the same. So what is it that so for example we have this case over here wherein all of them are adjacent. What about the case where they're not adjacent? We could still have something like this. And we have this, or we could have something along the lines of this. Similarly, now that we've covered two of these, what about there being three red lines? We'll just finish it up. It's the same. It is the same as this case over here, except we replaced red with blue. So there's a nice little symmetry over here, as you can see. So for example, we look at one blue line on the top, and then three red lines on the bottom like this. Similarly, we just look at this. Uh, we look at this, then we look at something along the lines of this, and finally this. Now, is it abundantly clear that we can obtain all of these via rotations from each other? Can you see, for example, that if I rotated this person 90 degrees, then we could get this person. If we rotate this square, this coloring 90 degrees, we get this one. Similarly, we rotate this one 90 degrees, we get this one. So to me, all of them are the exact same. They are this person, this one. Similarly, if I rotated this one 180 degrees, which is, sorry, this one 90 degrees, it's the exact same to me. Similarly, the case over here, a lot of these are essentially just equivalent because the same up to rotations to me. At the end of the day, what is actually important for us is to figure out how many of these are actually unique. So let's take a look. So we are 1, 2, 3, 4, 5, 6. So as is clearly visible, our so total number of say colorings is essentially 6. And we have achieved this by explicit enumeration. Does everybody agree with me over here? In any case, what we are basically going to be doing is looking at this situation again. But doing explicit enumeration is like really, really hard, honestly. Think about it. What if I had missed a case? I know that I haven't missed a case because it covers all 16 possibilities that were there. So for example, 4 for 8, 12, and then all 16 possibilities. But then what if I had missed a case? What would happen in that situation? Or for example, if I wanted to generalize this idea, what is it that I could have done? So for example, instead of two colors, what if there were three? What if there are 25? Say 100? What if it was the case that I wasn't working with a square, but rather say a pentagon? What if I was trying to figure all of these things out? In such a situation, we do require some sort of a general theory. And that is where, interestingly, Burnside's lemma comes to our rescue. So let me just state what the Burnside's lemma gives us. So the Burnside's lemma essentially just states that let G be a finite group, let X be a finite set, with G acting on X, with G and G acting on X. So what it basically states is we will denote, so this will denote the number of, denote number of orbits of X under this action. And now, then what we basically have is the cardinality of the number of orbits, this is what we're denoting it by, is equal to 1 over the cardinality of G, or rather the order of G, times uh, basically enumerating over G what we call the fix of G. That is the set of all points fixed by a particular element G. So we take the sum of all such cardinalities, sum of all such fixes, fixed sets, and then we take the average of that. So the average number of fixed points is essentially what we call is the number of orbits. That is what Burnside's lemma says. Now it seems like there's a lot of jargon here. Of course, I expect the audience to understand what groups are, what actions are. Also, one clarification is that we mean, when we talk about group actions, we mean left action. So G acts on X from the left, and also that we denote our group action by G dot X. So we will talk about G acting on X by the left. We will denote the action of G by G dot X. I hope that's clear, absolutely clear.
Yeah, maybe Chirag, you define left action.
Ah, yes, I'll do that. Okay, sir. So now, what is a left action? In essence, we say that G acts on X if there exists a map, say for now we'll call it phi, from G cross X to X. Mm, of course, taking G, this is a set map, taking G and X as this, which satisfies the following two conditions. Condition number one is that phi of the identity with some X, any X from the set. In fact, I'm going to write it this way, which should probably be a little better. For all X belonging to X, phi of E comma X, where E denotes the identity of G, is equal to X. And for all G1, G2 belonging to G, for all X belonging to X, we have phi of G1, uh, yeah, sorry, excuse me, phi of G2, comma X is equal to phi of G1, G2, X. I hope that makes sense. I'll write it in a different notation over here. All I'm really saying is we have that E dot X is equal to X, and G1 dot G2 dot X is the same as G1 G2 dot X. Does anyone have any questions over here? Please feel free to interrupt me at any point and ask me any questions that are present.
Yeah, maybe I have a comment. Maybe students can pause here for some time and go through some examples because of time constraint, he will not be giving examples, but you may explore some examples that will help you to understand the group action if you have not earlier seen this notation, group action. Or maybe
Yes.
also Chirag just define fix G before going.
Yes. I'm going to. I was going to do that. I mean, right after I define group actions. Right. So I hope you understand this. One particular action which is really simple to understand, for example, is just send everything to itself, basically. Or rather, maybe you could talk about G acting on itself, and you look at the group G itself with via left multiplication. That is one of my favorite actions. So you could look at some examples in your own time, and I highly suggest that you do so because it's a very fascinating theory to me. But moving beyond that, let me define some other things which are really important. For example, for a group action, one more thing that we look at, which is really important, is what we call what we call the fix of G. So now for every G in G, we define the fix of G as this set of all x in x such that G dot x is equal to x. So in essence, what is happening is that G dot x fixes G basically fixes x. So the idea of group action is that this over here, this whatever is on the left, the group acts on x very specifically. It basically takes an element over here, acts on this element over here, and produces another element over here. We'll see why that is important. So for example, if we go back to our coloring example, over here, the set that we might take would be something along the lines of what is the possible coloring. And we could basically get a group to act on this specific coloring so that it could rotate by 90 degrees and give you this coloring. You could act on this one by the same rotation by 90 degrees and give you this coloring. Is that all right for everyone? All right. Now, this is one set that we define. Another set that we define, which is very similar to this, we define it for every x in x, is the set stabilizer of x. This is basically now what we do is we collect all g in g such that g dot x is equal to x. Now, what we are really doing over here is in some sense this a very similar thing to what fix of G does, but this time we're doing it for the elements of X itself. So we figure out which are the group elements which fix G over here. So we figure out which are the group elements which fix X over here. We figure out all the ones which don't really do anything to X. It just sends X back to itself. And in a similar vein, we also look at something called the orbit of X. So the orbit of X is actually quite interesting because we basically, this is how we define it. It is basically G dot X. We just look at where X can go under this action. So we look at all G dot X such that G belongs to G. So, it's a question of where can X go? From here, starting from, for example, X itself. So, and interestingly, my question for all of you is that are any of these sets, for example, empty? That is my question for everybody. Can you tell me whether fixed G is, can you tell me fixed G for some G, for example, what is the fix of identity? Given that our group action satisfies the first property. So the first property, what ends up happening is that fix of identity is just the entire the entire set X basically, because E dot X is equal to X anyway. In any case, similarly, the stabilizer of X is not empty because you have the identity, and the orbit of X is not empty because you have X itself, which is present. So none of these are empty sets. Another small sort of result that we're going to be using for our proof of this theorem is what we call the orbit stabilizer theorem. And this is a fundamental result in group theory, in the theory of group actions. which is used everywhere, as a matter of fact. So what the orbit stabilizer theorem tells me is that for every x belonging to x, we have the same situation over here. For every x belonging to x, you have the cardinality or the order of G is equal to the order or the cardinality of orbit of x and the order of stabilizer of x. This is a fundamental result in the theory of group actions. I would suggest that you take perhaps a minute to just go through whatever I've written. And if you have any questions, please feel free to ask. All right. If no one has any question, I'm going to proceed further. So, how, for example, do we apply the idea of the Burnside's lemma to our problem that we just stated? Let's get back to actually looking at the problem over here. So let's get back to, for example, looking at how do we exactly apply all of these things. So as I said, the way you would look at, for example, the group over here, the way you would look at this is, for example, just look at this set. Say, we define our x to be, and this is our first example, so I'm going to do it this way. So we define our x to be the set of all so-called colorings of the square. It's a very how to put this? It's a fairly intuitive definition, but I'm sure I hope you understand what it is. And since we're looking at rotations very specifically, let's see what sort of rotations we can sort of look at. Now, if you look at it carefully, the way I have drawn all of these, you can see that a square itself can be rotated 0 degrees, which is basically you do nothing. It can be rotated by 90 degrees, wherein you start off with this person, then you go to here by rotating it 90 degrees. You rotate like this, then you rotate like this 90 degrees, and then you rotate like this. 90 degrees is possible, very much so. And much like that, you can also rotate it 180 degrees. Wherein you basically just start over here and you get the same sort of, you can rotate it 180 degrees wherein you start here and then you reach here, for example. And similarly, you can reach this person over here by 270-degree rotation. Now, why am I stating all of these is because the idea is that what we're really doing is we want to figure out the number of possible orbits of X. Now, how do we exactly do that? We basically, I'm sure you can understand by the way I've defined group actions, is you start off with something and you rotate it over here. So let me just do it for this example specifically. Right. So now let's look at our group being this group of rotations, which is basically I'm going to denote by R0 degrees as the group with the do nothing symmetry, so to speak, wherein you don't do anything. I'm going to denote by R90 as the 90-degree rotation. R180 I'm going to denote by the 180-degree rotation, and R270 is the 270-degree rotation. Now, what happens if I had defined R360? Well, that is just the same as the R0-degree rotation over here. So now let's go back to what we have and see whether we can actually get these ideas. So for example, if I have the if I start from this person over here, if you just start from this one, then we start off with this idea, this sort of coloring. We can rotate it 90 degrees to get this coloring. If we rotate it 180 degrees, we get this coloring. And if we get if we rotate it to this color, this rotation over here, this is basically a 270-degree rotation. I hope you can all see that. This is very geometric. That is the interesting bit about it. In fact, I'm sure you can all see that the way I've defined this is basically you're looking at the orbits of all of these. So orbits of our so-called representatives these specific cases. So the orbit of this under this specific action is essentially the these all four of these. I hope you can see all of that. So now let's calculate. All right, and now look at how we would solve this using group actions. The action on this is, we define this as by basically g dot x is equal to, and I'm just going to write it out, but there is a way to sort of write it in a little more perhaps standard fashion. Is that we rotate, is that we act, is that we basically do the rotation on to the rotation on abysmal handwriting on the X coloring. So to give you an example again, suppose I had started off with this. If I had started off with, for example, this one. Then, for example, the R0 rotation. So suppose I was rotating it by, say, the R0 rotation, that would just be this guy, the same sort of coloring. It would be the exact same coloring. However, suppose I was rotating it by, say for example, I was rotating this one. I'm going to draw it out again. I was just rotating it by this R 90 degrees. Then it would just be this one. And similarly, we look at this. We look at this and we look at the R 180 degrees rotation. So in 180 degrees rotation, this one becomes this one. And we essentially flip the entire thing in some sense. And finally, we look at this one. This is the R270 degree rotation. Now in R270 degree, this person over here goes to 1, 2, and 3. So it goes to the bottom. So I'm going to draw the bottom over here. And we have the rest like this. Now, as is clear, this essentially just looks at, we basically have the orbit over here. Now, what we need to figure out as the number of, we need to figure out how many representatives are there. And so that gives you the number of orbits in some sense. So we need to figure out the number of orbits that are present for this specific group action. So how do we do that? Let's look at, again, let's look at all of the rotations and let's look at Burnside's lemma, which basically gives us a tool to figure this out. Now it is clear that we know the cardinality of G, or the order of G. It's very clear that we know that. So all we need is this side of the specific equation, this fix of G, which is required. So let's look at which elements are fixed by all of these. Let's look at the specific fix of G. So for example, what is the fix of R0? Yes, this is a do nothing symmetry. This is basically the one where you do nothing. What this does to you is that you basically just have any sort of coloring that you have. It is fixed by this guy, right? It is essentially just fixed by this guy. So it is essentially the entirety of X. Now every coloring is fixed by this. So you just have the entirety of X, which is there. because any coloring that you have under the do nothing symmetry stays fixed. It is the exact same. Similarly, suppose we look at the R90. Now, here is where it becomes very interesting. When you look at the R90 symmetry and the R90 sort of the R90 specific group, the R90 specific element, what essentially ends up happening is that we want squares which are the same. So, for example, this square is the same for is not the same as, so for example, if you have one side which is like this, if you have one side like this and I rotate it by 90 degrees, you have this is what happens. These two are not the same elements. So for example, I wouldn't count this one as one of the, so this for example is not fixed by this guy. What we notice is that since we rotate it by 90 degrees, what we notice is that the top should be equal to the to the right side. Also, one more clarification: we rotated clockwise, anti-clockwise. Oh, sorry, clockwise. I should have clarified that initially. We rotate to the right. The top should be equal to the right, and similarly, like this, the right should be equal to the bottom. The bottom one should be equal to the left, and the left one should be equal to the top. What I mean by all of these is this, in a square, you have the top, you have the right, with the bottom, and you have the left. So I want these guys to be equal to each other. That's the only way, right? Because since we rotate, top goes to the right, so it has to be equal to the right from the start. The right one goes to the bottom, so it has to be equal to the bottom. The bottom one goes to the left after the rotation, and it has to be equal to the left one, and the left one goes to the top, so it has to be equal. So in essence, for this specific fix, we want all four sides have the same color, have same color, same color. And now, how many of these are present? We essentially just have two of these. In fact, I'm going to explicitly make these just for clarity. I'm going to erase this for the sake of clarity. So, which are the ones which we want? We want the ones which have the same sort of color. Excellent. Similarly, let's look at the case of fix of 270 degrees. If you think about it, it is essentially just R90, but instead of clockwise, anti-clockwise rotation. So if we apply the same idea, we still have, instead of anti-clockwise, this time what we would actually require for R270 is that we want the top person. So I'm going to draw a square over here. So this is the top, this is the right, this is the bottom, and this is the left. So the top one goes here, the left one goes here, the bottom one goes here, the right one goes here. So again, we need the exact same situation. We have the exact same situation over here, simply because we want the top to be equal to the left to be equal to the bottom one to be equal to the right, and the right one to be equal to the top. So essentially, it is the same exact people. So finally, we look at the R. We looked at R90, R270. We have looked at R0. Let's finally look at R180. Now, in the case of R180, it's quite interesting actually, because you could have that, when you, for example, when you have R180, when you have two of them equal. So you want basically the opposing sides to be equal. So for example, something like this and this, you could have just read over here. You want the opposing sides themselves to be equal, very specifically. And once you rotate it, you would have things like this guy. So if you rotate it by say 180 degrees, what do you have? You just have this, right? R180. Just have this. Now, what do we exactly need? We need that the opposing side should be the exact same, right? Now, to get the opposing side to be exact same, at the same time, there is, if you think about it, there are two colors which are possible over here, and there are two colors which are now. If you want, we want the top and bottom to be the same, and the left and right to be the same. Now there are two possibilities for the colors here, and two possibilities for the colors over here. So this gives us 2 times 2 is equal to 4 possibilities. We have to write the cardinality very specifically. So now we have everything that we require, and let's see if we actually managed to figure out the same answer that we got before. So now what we have is the cardinality of fix of R0 plus the cardinality of fix of R90 plus the cardinality of fix of R180 degrees plus the cardinality of fix of R270 is just equal to.
Okay, so Chirag, like how much time you will take after this?
Ma'am, I'll do this example. I'll do a small generalization, and
Okay,
I think I'll basically maybe 15 minutes, maybe 15 to 20 minutes. All right.
15 to 20 minutes.
Maximum. I mean, this is
Okay,
also
okay,
like
fine.
yes.
Okay.
So in total, we have sort of in total right now we have what is fixed of R naught is the entire set X, which is basically 16. The cardinality of that set is 16. Then we have that fix of R90, which we figured out to be 2. Similarly, fix of R180 is 2. And finally, R27 for R270, we figured it out to be 4, which gives us the total of 24. Now, applying Burnside's lemma, the number of possible orbits over here is 24 divided by the cardinality of G, which is equal to 24 divided by 6, which is equal to 4. Does that make sense for everybody? Sorry, 24 divided by, sorry, cardinality of G is, I made an error here. 24 divided by the cardinality of this, which is 4, which is 6, which is the exact same as our enumeration before. So in essence, what we have seen is a beautiful application of Burnside's lemma into solving this problem of counting objects up to rotational symmetry, up to rotations. And that to me, for example, personally, is extremely beautiful because and also extremely powerful because now I can give a lot better estimates and a lot better counts of what would be important and counts of configurations up to symmetry and specifically rotational symmetry. So since we have a theorem, we might as well do a proof of it. And I really like this proof because the first time I saw it, I was, really, enthralled. Honestly, I was really puzzled because I did not anticipate the proof to be that simple. So here is what we are going to do. We are going to be looking at a very specific table. We're going to be constructing a table, and we will assume we'll prove this statement, which is that let x is equal to x1 up till xm be a finite non-empty set. Let g is equal to g1 gn be a finite group. I mean, I've stated the gn, but I'm just stating it for brevity, for being verbose. Let G be a finite group acting on X. Now, what we basically have to prove is that denote number of orbits of X under this action by X by G. Then we just have cardinality of X by G is equal to 1 over mod G summation G belonging to G fix of G. Something we've stated before, but now we're going to prove it. So what is the proof of this? Let us look at this nice sort of table that we construct, which is basically we're going to write out all the xi's over here. Xm, and we'll denote identity by G1, for example, and which is going to write out all the group elements in the columns here. So say Gn. Now, how do we fill this table? What is this table filled by? This table specifically is filled by 1 if gi dot xj. So what I'm going to write it is as, we look at it from a matrix notation perspective, aij is equal to 1 if, denoted like this, is just 1 if, excuse me, yeah, gi dot xj is equal to xj and 0 otherwise. So as is clearly visible, for example, for identity, this would be 1, this would be 1, this would be 1, this would be 1, etc. for all of them. And similarly, for over here, we'll fill it by either 0 or 1. Since by the properties of group action, this is all defined. Once we fill this table, once we are done with that, we will look at what the totals are specifically. I'm going to erase this from here and write it on the other side. Once we fill this table, we're going to look at we're going to add these entries up, and we'll see something interesting. So here I'll just write it as aij. Our table is very specifically aij is equal to, again, equal to xj and 0 otherwise. Yeah. So now let's look at what the sum of these is. Let's write the totals over here. So the sum of this is basically g1 dot x1 is equal to 1, g2 dot x2 is equal to 1. This is going to be equal to 1 if and only if over here. Why? Okay, here is the question. Let's look at this. So g1 dot x1 is equal to 1. G2 dot x1, suppose this will be 1 only if g2 dot x1 is equal to x1. Similarly, say g5 dot x1 is equal to 1 is going to be 1 only if g5 dot x1 is equal to x1 itself. So we only have a 1 here if the group element on corresponding to that specific row um, belongs to is basically in the stabilizer of x. So basically what this gives us is the stabilizer is the card, yeah, or rather the cardinality or the order of the stabilizer of x1. And similarly, in general, what we have on this side, and I'm going to use a different color for this. What we have on this side is that this basically gives you the stabilizer of xi in general. Similarly, if you look at this side of the, look at, what this is basically what the column addition looks like. What about the row sum? What about the row sum? So now we have that g1 dot x1 is equal to 1 only if g1 x1 is equal g1 dot x1 is equal to x1 itself. Similarly, g1 dot this g1 x2 column, this cell is equal to 1 if and only if g1 dot x2 is equal to x2. So in essence, if g1 fixes x2, then we have a 1 over here, otherwise it's a 0. So in essence, what we really have is the cardinality of the fix of gi, which again we're going to use a different color for with use orange. Yeah. For the fix of say g1 over here, and similarly in general fix of gj. Now if you add all the column and the row sums, you add from you either add horizontally or you add vertically. It doesn't really matter because they should give you the same answer, right? That's the idea. So regardless of which side you add, it should give you the same answer. Now from the left hand side, we have that this is equal to the summation of all, and I'm going to denote this by yellow, the summation of all stabilizers in X, which is equal to the cardinalities of the summations. Oh, sorry, summation of the cardinalities, which is equal to the summation of all fix G. All right. Now, with that, what essentially ends up happening is we have shown with this proof till now is that the summation of these cardinalities is equal. But let's look at this a little more carefully. The right hand side by the orbit stabilizer theorem, which of course works because g and x are finite, is the same as the order of g divided by the cardinality of orbit of x. Now, here is where it gets very interesting. From here, we have, now this entire thing implies 1 over the cardinality of g, g belonging to g, fix of g, is equal to the summation x belonging to x, 1 over the orbit of x. Correct? Now, what can we do? Now, we obviously have the left hand side that we wanted, but what can we do about the right hand side for this situation? The right hand side for this situation, what we're basically going to be doing is something which uses some results on orbits, which is the fact that orbits essentially partition the set X itself. No, you don't like no an element cannot belong to two different orbits. That is one thing. Another thing is that every orbit is non-empty because it contains, the orbit of an element contains itself, and the union of all orbits gives you the entire set. So using those ideas, what we basically have is that suppose we take A inside our set X minus G, which is basically which we used for denoting the cardinality, and this basically is just one of the orbits. A is one of the orbits, and we just take all the Y inside A such that 1 over orbit of Y specifically, because the orbits divide the set in such a manner, these two summations are the exact same. However, what essentially ends up happening, in fact, actually, I can write it in a better manner, is that we basically end up looking at what we call the transversal of this set. Okay, let me just recap what just happened. Um, so in this situation, what we have is that since the orbits partition the set, we can take one identity, one representative, and we basically call that the transversal. The transversal of X, of X, of this partition specifically. So we basically take the transversal, and each of these elements inside the transversal is the representative of one particular orbit. And now once you take this X, all you really have to do is that you take all the elements in the orbit of this X and you just add them up, and you just add these cardinalities up. Why are these two the same? Because all we've really done is that instead of counting every orbit and every X, you've just taken the representative specifically, and then to each representative we have taken all the elements of the orbits inside the orbit of that specific X, and added this specific summation, which is why these two are equal. Any questions at this stage? Because this is the crucial step. Does everybody understand what has happened? All right. So now here what we do is that after we have the transversal here, see, all of these belong to the same orbit, right? So at the end of the day, it is going to be the cardinality is going to be the exact same, because if an element belongs to a particular orbit, the cardinality of its orbit is also the same as that, because the orbits are exactly the same. So suppose X belongs to the orbit of Y, then the orbit of X is equal to orbit of Y. Therefore, the cardinality of orbit of X is equal to the cardinality of orbit of Y. Now, since we pick all the Y inside the orbit of X, the cardinality of each of these is essentially just orbit of X. And that essentially, by an orbit of X, all of these is an orbit of X, which is the exact same as, which basically is the exact same as. Now we basically just have orbit of X representatives, and this is a constant, so we add them orbit of X times, and we just get summation X in the transversal 1. Now if X is in the transversal, this specific summation will basically have that we essentially have the number of terms in this summation is the same as the number of orbits, because those are the number of representatives that we take in the transversal. So this basically gives us cardinality of X by G, which is what we wanted initially. And that, I think, finishes the proof. Any questions at this stage? Please feel free to ask. All right. So now what we're basically doing is that we have understood Burnside's lemma and we've applied it to a very small problem. What my plan is that I'll apply it to one more problem and essentially show you the power of the lemma specifically when we try to generalize the problem that we just had. So now let's take the same square that we had, and instead of two colors, instead of two colors, let's just suppose there's n number of colors, some, but n colors specifically. What do we do in that situation? Now here we can't specifically enumerate all of them. What if n was 100? Then we would have like so many. We would have to check 2 to the or rather n to the 4 possibilities, which could be like n to the 4 in this situation is really big basically. So now what we have to do is that, because if n was something like even 10 for that matter, you would have something like 10,000 possibilities, which is a lot to check. So instead of doing that, let's apply Burnside's lemma and apply the same idea which we basically used, and look at the specific fixes over here. So for example, we would have the cardinality of the fix. So this would be the same as all possible permutations. Sorry, all possible colorings. If suppose you basically just took all possible colorings that are there, regardless of rotational symmetry. So it would just basically be n colors for this side, n colors for this side, n colors for this side, and n colors for this side. We have the product rule. We just have n to the 4 here. Now, suppose that now we want to look at, say, fix of R90. Here, what we basically have is that uh, we fix one side, as we noticed, we fix one side. Sorry, not even fix one side. We notice that all of the colors in the case of R90 should be equal. We fix one side and we saw that uh, because of that side, every color, every side should be the exact same. Every side should be the exact same color. Therefore, since we want all of them to be exact same and there are n possible colors, there are n possible squares in this situation. Moving on, similarly, we do the same exact analysis for our 270, and this gives us n colors over here. And finally, the hardest of them all, which is the R 180 degrees rotation. Now, in this situation, as we reasoned before, we need a total, we need basically we need basically the rotations where the opposite sides are the exact equal. So since it's the same exact idea, wherein this side should be the same color as this and this side should be the same color as this. In that situation, and these colors may or may not be distinct, by these colors may all be same as well, which is not an issue. So what in that situation, it could also be that all of them are red, for example. So in that situation, we have n choices for this color and we have n choices for this color. So applying the product rule, we have n square choices. Now adding all of these up, we basically just have that the cardinality of x by g in this situation is equal to the sum of 1 n to the 4 plus n plus n plus n square divided by the cardinality of the group G, which is 4, which is in essence what we have shown is the number of possible colorings of a square by n possible colors is equal to n to the 4, and I'm going to write it this way, plus n square plus 2n divided by 4. With that, I believe there are no more examples that I'd like to share, but I would like to give a few exercise problems, which I think will enhance your understanding of this. So, I mean, first exercise problem, as always, is generalize. You know, do it with, say, a pentagon, for example, or any number of sides. Do it with any number of sides. Do it with and in that case, the rotational group and all will also change quite a bit. It would be very interesting to see that. Here is an interesting question which I wanted to solve today, but because of time constraints, I won't be talking about. Is the idea of suppose you have these, you know, you have a p-sided, a p-gon. We assume p is greater than 3, oh sorry, greater than 2. Suppose you have a p-gon. So for example, something like this. This is a triangle. This is an equilateral triangle. This is a regular 3-gon, so to speak. The regular 4-gon. And you are coloring the sides of these guys. In fact, what you would do is, suppose instead of if you had a p-gon and to that you attached beads, very specifically beads like this, then how many possible colorings are present? For example, if I was doing it like this, how many possible such colorings are present in this situation? To calculate that, you can use Burnside's lemma. Burnside's lemma. And what you will find is, interestingly, that this would be equal to something along the lines of this. And also, we assume that P is prime. That's extremely important. P prime. And you want to color it with A colors. We'll find something along the lines of this. This is the number. Why is this important? Because this implies that P divides this number specifically. P divides A plus P minus 1 times A. Which then implies that A to the P minus A, or rather A to the P plus P minus 1A is congruent to 0 mod P. Which then implies that A to the P is congruent to A mod P. Interestingly, we have arrived upon Fermat's little theorem. So we have connected group theory to combinatorics through this specific lemma. Then we connected, and with this specific example, we can connect combinatorics to number theory. And I think, in my opinion, that is one of the most beautiful applications of the Burnside's lemma. With that, I'd like to thank everybody for attending and listening to my talk. And I hope I can get more opportunities like this. Thank you very much, VSSP, for this opportunity.
Okay, thank you, Chirag. So, do anyone have any other questions?
Yeah, maybe not a question, but I appreciate the way he linked all three branches. So for viewers, I would like to recommend that Professor Kumarsan has explicitly developed this group action theory in his YouTube channel. You may visit it. It might be helpful. That's all.
Okay, thank you, Chirag, for your presentation.